In this lesson, we're going to be look at a few different types of applications in addition to just the triangle application that we saw in the last problem. The first thing we want to discuss is something referred to as bearing. Now, bearing is an application that's used in navigation when you're sailing at sea, when you're flying a plane, to where you can determine which direction you're actually traveling. Now, there are two different types of bearing, or two different methods of describing bearing within a problem. The first method is if an angle or a bearing is ever given by just being told a particular angle, for instance, 164 degrees. So perhaps an application would say the bearing is 164 degrees. We know that that always means start by pointing north, which is vertical, straight up. And you're going to turn counterclockwise 164 degrees. Now notice that this is different from a standard angle of 164 degrees, where you would be pointing in the positive x direction and rotating almost to 180, which would be back here in the second quadrant. But this isn't bearing. When we're referring to bearing, we always start by pointing north. So a bearing of 304 degrees would mean start by pointing north and turn like a clock 304 degrees around. Now, the second method is used if you just want to be able to describe an acute angle. And so the way that we do that is we always either point on either a north or a south line. So the starting point here would be that we might say for this one, we're going to start by pointing north. And we are going to turn 42 degrees in this direction, which is towards the east. So we read that as north 42 degrees east. We could also start by pointing south. And now it says start by pointing south and turn 31 degrees towards the east. So keep in mind that when we're referring to a compass, this is north, this is south. We live on the west coast in California, and here is the east. And so notice that this would be south 31 degrees east. If we look at the next one, notice that it's still pointing south to start, but notice how it is turning now towards the west. So it's south 40 degrees west. So you can actually see that this is technically northeast, which is in the northeast direction. This is southeast in the southeast direction, but it's telling you how far in the southeast or how far in the southwest direction. So this last one, you would be, again, starting by pointing north and turn 52 degrees towards the west. So this would be north 52 degrees west. So you can see that these are just a couple of different ways to describe bearing. And so both of these are going to be used in applications for triangles. So here is an example of a problem involving bearing. And the most important part of any application problem in trigonometry is to draw an accurate diagram, to draw an accurate triangle. And so most of the time should be spent at the very beginning, making sure that everything that's stated inside of the problem is drawn on your picture, okay? Now, by the time we're done, we should have a triangle that's going to have us solve for a particular aspect of that triangle. So here it says a ship leaves port. So we got to start off by drawing where the port is. So the port, let's just say, is right here. And it says he's sailing on a bearing of north 47 degrees east. So we first have to draw our north line. So the thing is that he's not actually sailing north. So that's why I'm putting my north line as a dotted line, okay? But now it says that it's going to turn towards the east, which is turning this way. We've just got to turn 47 degrees. So keep in mind that if this is 90 degrees, if this is straight east, 47 degrees would be somewhere a little past halfway in. So we're going to say that this right here is the angle of 47 degrees. So north 47 degrees east. And it says that this ship sailed on a bearing of north 47 degrees east for 3.5 hours. So be very careful, because I'm not going to put 3.5 hours on here. 3.5 hours is not a distance. That's an amount of time. So we're going to hold off on doing anything with that at this point. But then it says it then turns and sails on a bearing of south 34 degrees east. So now it's at this point. So we've got to draw another bearing line. Okay, so it's pointing towards the south and it's turning towards the east. So it's got to turn 43 degrees towards the east. So that means it's going to start by pointing south and turn towards the east. So we've got to draw the angle of 43 degrees, which is approximately a little less than halfway in. Okay, and this is traveling for 4 hours. So it looks like that line's probably going to be a bit longer than the other one. Okay, because here it was traveling for 3.5 hours. This one was traveling for 4 hours. Okay. Now apparently it's gotten to somewhere over here. So we now need to fill in our picture here. So from the south line towards this bearing is an angle of 43 degrees. And finally, if the ship's rate is 22 knots. Now knots is a unit of measurement similar to miles per hour, except it's nautical miles per hour, which means there's a speed on the ocean, okay? So when we try to figure out the total distance that was traveled in each, let's just call this first one trip 1. I should be able to see that the distance, let's call it distance 1, is equal to 22 knots, which is our speed, times 3.5 hours. And that gives us a total of 77 miles. So now I can go back over here and I could fill in that this distance is 77 miles. And then I got to figure out what the second distance is. So let's call that trip 2. And we could see that in that case, his speed is 22 knots, but now he's traveling for 4 hours. So now I know that 22 times 4 is 88. Okay, so we could fill in 88 miles over here. Okay, well, the final question then, which is always the last sentence here, it says, find the distance that the ship is from port. We'll notice that that distance is going to be this distance from port to where he currently is. So let's call that D. And now this is a great diagram. We can see our dotted north-south lines from where we're actually traveling, because we had to draw those in order to draw bearing. We see all of the information given in the problem filled in. So now it's just a matter of starting to figure out how we can start to work through this, okay? Now, what you're gonna notice right now is that we have to be given a right triangle in order to solve this. If we don't have a right triangle, then we can't solve it yet because we don't have the method for that. So this is going to turn into a right triangle, but it's not obvious at this point that it is, all right? So why don't we go ahead and try to use the information we have to start filling in some other information. So we see, first of all, a north-south line over here. We also see a north-south line over here. So those two lines are parallel, cut by this transversal. So by our angle relationships that we learned a while back, that must mean by alternate interior angles, this angle right here is 47 degrees. And now we see that 47 and 43 gives me a total of 90. And so since this angle right here is 90 degrees, I now have a right triangle. So because it's a right triangle, I'm given two legs of the triangle. So I can use the Pythagorean theorem in order to find the last leg. Okay. All right, so I've got 77 squared plus 88 squared is going to equal the hypotenuse, which is d, or the distance, squared. By squaring each of these values, we get 5,929 plus 7,744. Add them together and we get 13,673. Okay. But that's still not the distance until we square root both sides. And would we do so, we square root 13,673, and we get approximately 116.9. Now notice these are only two significant digits. So although we get an answer of D equals 116.9, that's four significant digits. So that's too accurate. So we need to maybe round it to 117. But notice that that's also too accurate, okay? Which technically means that this answer should be rounded to the second decimal spot, okay, or the second digit, which would mean that we would say approximately 120 miles. Okay. However, I'm going to be honest here, and you know, I'm not too much of a stickler for significant digits. So if you end up writing that this is 117 miles, I'm actually okay with that. Okay. So 117 miles is the distance. So you could see that this problem turned out to not be so difficult once we had the diagram. The hard part of a lot of application problems is drawing the accurate diagram. So really take your time, and when you're drawing your north-south lines and your east-west lines, just make those dotted lines so that you can have a reference of where to draw your angles. Now in this next example, this has nothing to do with bearing anymore, but I can see that it's giving us something related to an angle of elevation. So again, it's going to relate to some sort of triangle. So let's try to take our time drawing this diagram as accurately as we can. So it says Francisco needs to know the height of a tree. All right, so yeah, you could draw a tree, or you could just draw a vertical line that represents the tree. Right? So let's just say that I drew this vertical line, and that is representing the tree. Since we're trying to draw a triangle, that's totally acceptable. So let's just say that that's the height that of the tree. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. So if you were looking from the ground, say from right here, or from right here, or from way over here, notice that the angle of elevation would be different depending on where you are. So he's at some location where the angle of elevation is going to be 36.7 degrees. Now it doesn't have to be accurate, but you simply draw a line to a particular point in order to see what where the angle of elevation is going to be. Now keep in mind that an angle of elevation is always from a horizontal and looking upwards. So the angle of elevation here is from the base up to the line of sight to the top of the tree. So we know that this is 36.7 degrees. It says he then moves back 50 feet. So that means that he's moving away from the tree. Otherwise, if he was to move this way, then he'd be moving towards the tree. So he's moving back, which means he's somewhere back here. And now he looks at the angle of elevation. He then moves back 50 feet. So let's just go ahead and draw that distance. So we know that this distance right here is 50 feet. And now he sees from the second point, the angle of elevation to the top of the tree is 22.2 degrees. So again, from the base, looking up to the top of the tree is 22 degrees. So considering we now have this triangle with the blue, green, and orange line, where this right here is 22.2 degrees, it's now asking us to find the height of the tree. So that's the variable. We don't know the height of the tree, so let's label it h. Now that's our diagram, but the thing that should be a little weird to you is that this triangle right here is not a right triangle. Secondly, I see that this triangle over here, okay, that this height, the h, or the height of the tree, isn't even part of a triangle. So this is where you have to start to think a little bit differently here, where if I were to continue by drawing this line connecting here, I've now created a right triangle. The tree is vertical or perpendicular to the ground. And so now this is the scenario that we have. We don't have any sides of this triangle, but we do have an angle inside of the triangle. But we also should see that there's a triangle inside of another triangle. There's this triangle here, but then there's also this entire triangle here. They're both right triangles. So we should be able to use some information here in order to find what's missing. One thing you can notice about the height of the tree is that the height is the opposite side of 36.7 degrees in this triangle, but it's also the opposite side of 22.2 degrees. So if we think about what ratios involve the opposite side, that would be sine, which is opposite over hypotenuse, or tangent, which is opposite over adjacent. So considering there was nothing given about the hypotenuse of either one of these triangles, and we don't really care anything about the distance from the observer up to the top of the tree, the most obvious, the most logical next step would be to think, well, maybe we could use something relating to the adjacent side. The adjacent side to the 36.7 degree angle would be right here. But again, we don't know what that is. So we know that this is going to be x feet, but we don't know how far. Okay, so let's just call it x. And now it looks like we have a couple of relationships we could come up with. I see one relationship for the blue triangle, which would show that tangent of 36.7 degrees is equal to opposite over adjacent. Now, one minor little problem right here is that we still have two variables. So now why don't we go ahead and take a look at the large triangle, which is this whole one right here, and think of that as a whole right triangle. If we were to look again at tangent, okay, tangent is opposite over adjacent, so tangent of 22.2 degrees, the really narrow angle, is equal to opposite over. But now let's look at the adjacent side. The adjacent side is this whole side. So this is where we have to use a little logic to realize that if this piece alone is 50 feet, and I don't know this side, then I know that together it's going to be x plus 50. And now you should notice that we have a system of equations. This system of equations is two equations with two variables. So we just need to do whatever we can in order to solve for h. This is where our algebra skills should come into play. So if we cross multiply, we would see that x times tangent of 36.7 degrees is the value of h. But we should also see that if I multiply both sides by x plus 50, I get x plus 50 times tangent of 22.2 degrees is also equal to h. And so because both of these quantities are equal to h, we could actually set them equal to each other. So why don't we merge them together and realize that x times tangent of 36.7 degrees. Now keep in mind, tangent of 36.7 degrees is a number. But I'm going to keep it as is for as long as possible because I don't want to have to deal with a bunch of decimals up to 8, 9 decimal spots within my equation. I'm going to keep it in terms of tangent and then deal with that at the end. And so let's say that this here, since they're both equal to h, I'm going to distribute the tangent. And that gives us x times tangent of 22.2 degrees plus 50 times tangent of 22.2 degrees. So we're still trying to solve for x here. And so since x shows up on both sides, we're going to subtract this term over to the other side, which means that we get x tangent 36.7 degrees minus x times tangent of 22.2 degrees is equal to 50 times tangent of 22.2 degrees. Now, in order to solve for x, we're going to factor out that x. After that x is factored out, we could finally divide by this quantity. Again, keep in mind that this is a number. It's a decimal on our calculator. This is also a number. When I subtract them, it's still a number. So this acts just as if it said something like 3x equals 6. We simply divide by that whole quantity, and we get that x is equal to 50 times tangent of 22.2 degrees divided by that whole quantity of tangent 36.7 degrees minus tangent of 22.2 degrees. Now on our calculator, we could find what each of these values are. By putting each of these quantities of tangent 22.2 degrees and tangent of 36.7 degrees into your calculator, you get these values of approximately 0.408 for tangent 22.2 and approximately 0.745 for tangent of 36.7. When you go through the calculation here, this turns out to be an x value of approximately 60.497 feet, an x value. So that means that over here, this distance that he was away from the tree at the beginning was approximately 60 feet. Now you should recognize that we have the entire length. And we have the x value right here, which means that the only unknown is h. So we could find h by recognizing that it's x times tangent of 36.7 degrees. So let's take h then, which is x, or 60.497, times tangent of 36.7 degrees. Which gives me a final result of h equals approximately 45.09 feet. Or if we're using the significant digits from up here, we could see that this one gave 50 feet. So let's use 2 decimal spots, or I'm sorry, 2 digits. So we should be able to say that this is approximately 45 feet. So using just that information, think about this as a very practical application. I want to know how tall that tall tree is over when I'm camping. So I have a device that could tell me what the angle of elevation is to the top of the tree, and I measure off 50 feet and take the angle of elevation again. These are all measurable quantities here, and just based on that information, we were able to find out what the height of the tree is. So all application problems in trigonometry will be different from each other, but in many ways, they're going to be very similar because of the fact that they're all dealing with right triangles, and we can now deal with trigonometric functions in order to find the missing pieces.